Hey guys, welcome to Science 4.1b. Today we're going to be talking about something that we have talked about before, but not as much as we talked about surface tension, capillarity, and everything like that. So it's going to be more new and newer, I guess is the word, newer. And really, for some of you guys, it might just feel like complete new concepts because we really didn't dive too far into it the last time. Okay, so I don't know if you guys remember Pascal's principle. That's what we're going to be talking about today. Pascal's principle says basically, like, if you have liquid in a glass and you put pressure on that liquid, air puts pressure on the liquid. Now this glass is closed, so we say that for real the air is not getting into here at all, then the air pressure is not valid. However, that only happens in a vacuum. We know that when you suck out all the air pressure. But if you do put pressure on this liquid, that pressure is felt equally throughout the liquid, okay? It's not just on the top of the liquid or wherever you put the pressure. The liquid is felt all around it, and that may sound like, okay, who really cares? Well, it actually really helps a lot to know what will happen to force inside an object, what will happen to the area of certain objects, certain engineering inventions, because you can know that the pressure is constant throughout the container of liquid, okay? Today we're gonna talk about gravitational pressure. So not only do we have atmospheric pressure that's pushing down on a liquid always, it's gonna make it heavier, you also have the gravitational pressure, which is pulling it down to the earth, creating a lot of weight as well, okay? So like we talked about before, you go diving into the ocean, you're gonna feel a ton of pressure on top of you. What kind of pressure are you feeling? You're feeling atmospheric pressure from the air, and you're also feeling gravitational pressure, which is pulling you down, okay? And where are you feeling it? Just on top of you? No, you're feeling it all around you, okay? Because Pascal's principle says that pressure is even throughout, okay? That really helps a lot of scientists know how to create certain things that go down into the water or that go into certain fluids and liquids, to know that the pressure is throughout so that they can invent things that can hold the pressure throughout and not just focus on where they think the pressure is according to their hypothesis, right? So it is a very important list of concepts that we're going to go over today. And then, so I'm going to introduce what you need to be looking for your notes. And then I'm going to put in 2 videos from Khan Academy. One, I really want to introduce you to Khan Academy if you've never used him before. This guy is a genius, okay? And you can learn a million concepts from him. So today you're going to watch 2 of his videos because it's part 1 and part 2. By the end of part 2, when you start to see that he's kind of repeating himself in part 2, you can skip to the next thing. But that's at the very end of it, okay? I'm not giving you liberty to just completely ignore it because it has very good information. And when you get to one concept, I'm not going to ask you to get information out of the book. I'm going to ask you to get information from that video. So there are going to be notes from that video because he explains it very, very well about hydraulics, which is a very abstract theme. Okay, so that's what we're going to be talking about today. So look at page 85. Look at page 85. Okay, I want you to write 4 sentences explaining gravitational pressure, including the 2 factors that affect gravitational pressure. So that starts on page 85 and goes over to page 86. 4 sentences on gravitational pressure, and including the 2 factors that affect gravitational pressure. Okay, then I want you to write 3 sentences explaining Pascal's principle on page 86. 3 sentences explaining Pascal's principle. Okay? And then, look at page 87. I want you to write 4 sentences about your opinion. This is your opinion. How do you think the faith of Blaise Pascal helped him be a better scientist? How do you think that the faith of Blaise Pascal helped him be a better scientist? This is a very beautiful little biography section that they give about him. Did you guys know that he died at the age of 39? And he did a bazillion things for science before he died at the age of 39. That's somebody that completely applies the verse, that's the verse of our school, Colossians 4:5, redimiendo el tiempo. Okay, he knew what God had called him to, he studied for what God had called him to, and he did what God had called him to. all before the age of 39, he gave a lot to science, okay? For hydraulics, you're not doing notes from the book. I want you to have at least 10 points, not a paragraph, list. That's totally fine, okay? List. You don't have to do a summary of the video. Just list 10 points that you learned from the video. That stuff is very interesting and very important to understand hydraulics, which is what we're gonna do practices on when you're done watching the video. So go ahead and watch those videos, get your notes, and then come back and I will do these practice problems with you so you can see how this math works.
Let's learn a little bit about fluids. So, and you probably have some notion of what a fluid is, but let's talk about it in the physics sense, or maybe even in the chemistry sense, depending on in what context you're watching this video. So, a fluid is anything that takes the shape of its container. So, for example, if I had a glass sphere, and let's say that we're in like let's say I completely fill this glass sphere with water. I was going to say we're in a zero gravity environment, but you really don't even need that. Let's say that every cubic centimeter or cubic meter of this glass sphere is filled with water. And notice, and then let's say that if I were to, and let's say it's not a glass, let's say it's a rubber sphere. If I were to change the shape of that sphere, but not really change the shape of the volume, and if I were to change the shape of the sphere where it looks like this now, the water would just change its shape with the container, right? The water would just change the shape with the container, and in this case I have green water. And the same is also true if I had, if that was oxygen or if that was just some gas, right? It would fill the container, and in this situation it would also fill the newly shaped container. So a fluid, in general, takes the shape of container. Takes shape of container. And I just gave you two examples of fluids. You have liquids, and you have gases. Those are two types of fluids. Both of those things take the shape of their container. And now what's the difference between a liquid and a gas then? Well, a gas is compressible. Which means that I could actually decrease the volume of this container, and the gas will just become denser within the container. So you can think of it as if I blew air into a balloon, you could squeeze that balloon a little bit. There's air in there. I mean, at some point the pressure might get high enough to pop the balloon, but you can squeeze it. While a liquid is incompressible. Incompressible. And how do I know that a liquid is incompressible? Well, imagine the same balloon filled with water, completely filled with water. If you squeezed on that balloon from every side, so let's say that, let me pick a different color. Let's say that I had this balloon and it was filled with water. If you squeezed on this balloon from every side, you would not be able to change the volume of this balloon. Actually, no matter what you do, you would not be able to change the volume of this balloon, no matter how much force or pressure you put from any side on it. While if this was filled with gas, and magenta balloon for gas, you actually could decrease the volume by just increasing the pressure on all sides of the balloon. And you could actually squeeze it and make the entire volume smaller. So that's the difference between a liquid and a gas. Gas is compressible, liquid isn't. And we'll learn later that you can turn a liquid into a gas and gas into a liquid and turn liquids into solids. But we'll learn all about that later. But this is a pretty good working definition of that. So let's use that, and now we're going to actually just focus on the liquids to see if we could learn a little bit about liquid motion, or maybe even fluid motion in general. Okay, let me draw something else. So let's say I had a situation where, let's say I have this weird shaped object which tends to show up in a lot of physics books, which I'll draw in yellow. This weird shaped container where it's relatively narrow there, and then it goes and kind of U-turns into a much larger opening. Let's say that the area of this opening is, let's say that this is A1, and that the area of this opening is A2. Right, and this one is bigger. And let's fill this thing with some liquid, which will be blue. So that's my liquid. let's fill it with some liquid. Let me see if they have this tool, if this tool will actually work. There you go. Look at that. I filled it with liquid so quickly. All right, and this wasn't, and this was liquid. This is not just a fluid. And so what's the important thing about liquid is that it's incompressible. So let's take what we know about force, actually about work, and see if we can come up with any rules about force and pressure with liquids, etc. So what do we know about work? Work is force times distance, or you can also kind of view it as the energy put into the system. So I'll write it down here. So work is equal to force times distance. And we learned in the mechanical advantage, etc., that the work in, I'll do it that I, is equal to work out, right? The force times the distance that you put into a system is equal to the force times the distance you put out of it. And you might want to review the work chapters on that. But that's just the law of conservation of energy, because work in is just the energy that you're putting into a system, right? It's measured in joules, and the work out is the energy that comes out of a system. And that's just saying that no energy is destroyed or created. It just turns into different forms. So let's just use this definition. So the force times distance in is equal to force times distance out. Force in, I'll do I like that, times distance in is equal to force out times distance out. All right, so let's say that I pressed with some force on this entire surface. So let's say I had like a, let's say it's like a piston. Let me see if I can draw a piston. What's a good color for piston? So let's add a magenta piston right here. And I push down on this magenta piston. Let's say I pushed down on this with a force of F1, right? And let's say I push it a distance of D1. So let me say, so it goes, that's its initial position, and say its final position. I'll do in a, let's see what color. The hardest part of these videos is picking the color. So let's say like after I've pushed it, the piston goes this far. So this is the distance that I pushed it, right? So this is D1. The water is here, and I pushed the water down D1 meters or whatever, right? So in this situation, my work in is F1 times D1, right? But let me ask you a question. How much water did I displace? How much total water did I displace? Well, it's this volume, right? I took this entire volume and pushed it down. So what's the volume right there that I displaced? Well, the volume there is going to be, so the volume that I'm displacing, so I'll say that the volume displaced has to equal this distance, right? This is like a cylinder of liquid, of liquid. So this distance times the area, right? Times the area of the container at that point. And I'm assuming it's constant at that point, and then it changes after that. So it equals area 1 times distance 1, right? Well, we also know that that liquid has to go someplace, right? Because what do we know about a liquid? Is that you can't compress it. You can't change its total volume. So all of that volume is going to have to go someplace else. So if this is where the liquid was, the liquid is going to rise some level. Let me say, let's say it gets to this level. This is its new level, right? It's going to change some distance here. It's going to change some distance there. And how do we know what distance that's going to be? Well, the volume that it changes here it's got to go someplace, right? You could say, well, that's going to push on that. That's all going to push, and that liquid has to go someplace. And essentially, it's going to end up. It might not be the exact same molecules, but that might displace some liquid here. That's going to displace some liquid here and here and here and here, and all the way until the liquid up here gets displaced and gets pushed upward. So the volume that you're pushing down here is the same volume that goes up right here. And so what's the volume? What's the change in volume, or how much? How much volume did you push up here? Well, this volume here is going to be the distance 2 times this larger area, right? So we could say volume 2 is going to be equal to the distance 2 times this larger area. And we know that this liquid is incompressible. So this volume has to be the same as this volume, right? So we know that these two quantities are equal to each other. So area 1 times distance 1, right? This area times this distance is going to be equal to this area times this distance. Area 2 times distance 2. So let's see what we can do. So we know this, that the force in times the distance in is equal to the force out times the distance out. Let's take this equation. I'm going to switch back to green just so we don't lose track of things. And divide both sides by, well, let's just rewrite it. So let's say I rewrote each input force. Oh, actually, I'm about to run out of time, so I'll continue this into the next video. See you soon. Welcome back. So just to review what I was doing in the last video before I run out of time, I said that, okay, conservation of energy tells us that the work I put into the system, or the energy that I put into the system, because they're really the same thing, is equal to the work that I get out of the system, or the energy that I got out of the system, right? And I said, well, that means that the input work is equal to the output work, or that the input force times the input distance is equal to the output force times the output distance. That's just the definition of work. And let me just rewrite this equation here. Well, if I could just rewrite this exact equation, I could say, so the force, input force, and let me just divide it by, just for kicks, let me divide it by this area. Because what I'm talking, the input here, I'm pressing down this piston that's pressing down on this area of water. So it's input force, and let me say that times the input area. Well, let me call this input. Let's call it the input 1. And let's call the output 2 for simplicity. So there's going to be some, let's say I have a piston on the top here. Let me do this in a good color, like brown. Brown is a good color. So I have another piston here, right? And there's going to be some outward force, F2. And this is the general notion is that I'm pushing on this water. The water can't be compressed, so the water is going to push up on this end, right? So the input force times the input distance is going to be equal to the output force times the output distance, right? This is just law of conservation of energy and everything we did with work, etc. So I just I'm rewriting this equation. So if I take the input force and divide by the input area, let me just switch back to green. And then let's say I multiply by the area then. And then I just multiply times d1. You see what I did here? I just multiplied and divided by a1, which you can do. You can multiply and divide by any number, right? These two cancel out, is equal to the same thing on the other side. F2, I'm not good at managing my space on my whiteboard. F2 over A2 times A2 times D2. Hopefully that makes sense. So what's this quantity right here? This F1 divided by A1. Well, force divided by area, if you haven't been familiar with it already, and actually if you're just watching my videos, there's no reason for you to be, is defined as pressure. Pressure is force in a given area. So this is pressure. So we'll call this the pressure that I'm inputting into the system. Pressure 1 times, and what's area 1 times distance 1? So that's the area of the tube at this point, the cross-sectional area times its distance. Well, that's equal to this volume that I calculated in the previous video, right? We could say that's the input volume, or V1. Pressure times V1 is equal to the output pressure, right? Force 2 divided by area 2, right? That's the output pressure that the water is exerting on this piston. So that's the output pressure, P2. And what's area 2 times D2? So this area, the cross-sectional area, times the height at which how much the water is being displaced upward, that is equal to volume 2, right? But what do we know about these two volumes? And I went over it probably redundantly in the previous video, is that those two volumes are equal, right? V1 is equal to V2. So we could just divide both sides by that equation, and you get the pressure input is equal to the pressure output. So P1 is equal to P2. So P1 is equal to P2 coming out. P2. And I did all of that just to show you that this isn't a new concept. This is just the conservation of energy. The only new thing I did is I divided, we have this notion of the cross-sectional area, and we have this notion of pressure. So where does that help us? Well, this actually tells us, and you can do this example in multiple situations, but I like to think of it if we didn't have gravity first, because gravity tends to confuse things, but we'll introduce gravity in a video or two, is that when you have any external a pressure onto a liquid, so onto an incompressible fluid, that pressure is distributed evenly throughout the fluid. And that's what we essentially just proved just using the law of conservation of energy and everything we know about work. And what I just said, that's called Pascal's principle. That if any external pressure is applied to a fluid, that pressure is distributed throughout the fluid equally. And another way to think about it, I mean, we proved it with this little drawing here.
Okay, so in that video, you were introduced to a million formulas, but I'm going to show you the ones that will apply to us on what we are doing in the practices today. Okay, so look at page 86. The practice 4.1a says a large glass jug of uniform thickness is completely filled with water and closed with a rubber stopper. The area around its opening is 0.0010 meters squared. So we have our area. By striking the stopper with a force of 45 newtons, how much pressure is added to the container at every point according to Pascal's principle? If there is enough force to crack the jug, where would you expect the glass to break and why? Okay, based on the information that we have, let's talk about where the glass would break first of all. Right? You have a jug. It's stopped with a rubber stopper. So there's a bunch of pressure left in here and you hit it on the top. Where is that pressure going to go? Well, it already tells you the pressure is going to go to the container at every point. So where would you think that it would crack? I had two possible theories. I would think that it would still start at the top and crack because while it is, and keep going because the pressure is throughout the whole thing, but you did actually exert the force right there. Or that it would shatter. That's what I always saw at the beginning of this study, even last year. That it would shatter because it would just basically explode because it couldn't handle all that pressure anymore on every side. Okay, so based on the information that we have, those are my two theories, and maybe you guys have different ones. Okay, that's what science is, right? Hypothesis, then experiment. So we would have to see. Okay, but how are we going to find what the pressure is? Well, if you look at page 87, it tells you that the formula for pressure is, according to Pascal's principle, force over area. So all you have to do is divide 45 by this, and you're going to get, maybe I already did it on my paper. No, not that one. 45,000. Okay, 45,000 pascals. There you go. Now go over to page 88. Let's do the practice. Here in the practice, it's going to say to use two different methods. We're not going to use two different methods. I'm going to show you the formula that we're going to get used to for Pascal's principle, which is going to be force input over area input equals force output over area output. This is a ratio. Okay, this is a direct ratio for those of you in Algebra 2 that were just studying this last week. When the force increases, the area increases. So the force input increases on the force output, then the area has to increase as well. Okay, so let's look at example 4.2. The hydraulic press shown in figure 4.7 has a small piston with an area of 10 centimeters squared and a large piston with an area of 100 centimeters squared. By the way, let's stop right there for a second. What are some everyday hydraulic presses? Hydraulic presses could be anything from when you pump gas at Petrosun. Okay, that's a use of a hydraulic press. When you're using the chairs that pump up and then they pump down, like especially in a salon or even in the office, you have chairs that go up and go down. What was I just about to say? When you take the thing that pushes a car up so that you can work on the tire or work under it, that's a hydraulic press. Trying to think of some more common everyday uses of a hydraulic press. That's all I could think of right now because it like went out of my brain. But so it's not just that we're learning about this weird shape of a thing that we like never see or anything like that. Okay, it's anything that you need to pump through something else. Factories even use it to like make things go down an assembly line to pump things moving forward to push it, okay? So hydraulic presses are literally, even though they seem like an abstract thing, they are used in everyday life, and so people that are inventing things for everyday life have to have a good understanding of it, okay? So we're just getting introduced to the formulas today, but it is a good introduction, and especially if you watched that video well and took good notes, it was an amazing introduction. Okay, so it says right here, use both methods described in the text to calculate the output force produced by an input force of 20. Okay, and this is going to be super simple. So we have an input force of 20, we have the area is 10. We're looking for the output force when the area was 100. Crisscross and multiply. You're going to go 20 times 100 divided by 10 is basically what's going to happen, and your answer is going to be 200. Okay, which makes sense, and it's completely has sentido because 10 increased to 100, so 20 must increase to 200. So it's a direct proportion. Okay, look at example or practice 4.1b. In 4.1b, we're going to have to refer to a little bit of information up above it, but I will show you what information we need to solve these problems. The first one says the small cylinder of a hydraulic press has an area of 15 centimeters squared. If a force of 45 newtons is applied to the small piston, what is the pressure within the large cylinder according to Pascal's principle? Well, we know that it doesn't really matter where the pressure comes from in this machine, it's going to be even throughout. So even though we have the area of the small piston and we have the force of the small piston and we don't know the area of the large piston, we can find the pressure because it's even throughout, no matter if you're on the small side or on the large side. So all we have to do is do pressure equals F over A. Our F is 45 and our A is 15, so that means our pressure is going to be 3 pascals. That's it. Everywhere inside that simple machine are going to be 3 pascals. Number 2 says if the large piston of a hydraulic press has an area of 500 centimeters squared, what will be the total force upon it if the pressure is 100,000 pascals produced by the small piston? Again, produced by the small piston. Pray on about that. It means that it's going to be even throughout, right? So the force is going to change and everything like that. But when we're talking about pressure, that's going to be even. So we can use this formula again. We already know that the pressure is 100,000. We're looking for the what? The force. We're looking for the force, and we have the area of 500, right? Okay, so then all you have to do is multiply this times this to get your force, which is going to be 1, 2, 3, 4, 5 zeros, 6, 7 zeros, 50 million. Okay, and then number 3. Okay, let's do number 3. By the way, number 2, I felt like I said something wrong, but I didn't, because the area was given for the large piston, and that's why it's okay to use that area to find the large force. Okay, so I felt like for some reason that I said that area was for the small piston, but it's not, because that would not have been the formula to use if it was. Okay, number 3, a hydraulic press has a small piston with an area of 0.8 and a large piston with an area of 60. So I'm going to go ahead, I already can tell we're going to be using this formula, and if I'm wrong, I can change it. So we're going to go 0.8 here, 60 here. A force of 150 newtons is applied to the small one. Determine the output force of the large cylinder under ideal conditions. Okay, so let's do that one first, and then if the input distance is 12, what is the output distance? Okay, and that's where we have to refer to the information above to get that, I believe. Okay, so here we go. We have 150 over 0.8 equals F over 60. Crisscross and multiply, and your F is going to be 11,250, which is a very weird F, but nonetheless, that is what it is. Okay, and then let's figure out if the input distance is 12 centimeters, what is the output distance? Okay, up above, look at the paragraph, and it says in the italics, right? The increase in force provided by a hydraulic press can occur only at the expense of distance. Okay, so you saw that on the video, right? He had a small tube over here, and then it goes into a larger one, right? And if he presses down on the fluid here with a large distance, it's only going to make this one go up what? A small distance, because of the area and the volume of the large piston, right? Okay, so basically what are we saying? That force and distance are inversely related. When one goes up, the other one must go down, okay? So in this case right here, the force went from 150 to 11,250. It increased bastante, right? So how much did it increase by? Take 11,250 divided by 150. It increased 75 times, okay? The force input times 75 equals your force output. So what are you going to do to your distance? You're going to divide it by 75 so that the inverse relationship completes itself. So you're going to take the distance that you have here. If the input distance is 12, you're going to divide that by 75. And you're only going to get a distance of 0.16. Okay? So while it moved 12 centimeters down, it's only going to move the water, displace the water 0.16 centimeters up. Okay? And that's how you do it. The rest is up to you. So let's review one more time. All the themes I mentioned before the videos, then you need to take the notes of the video. Make sure you do these practices with me on your paper. And make sure you talk about Blaise Pascal that I asked you to. And then you're going to do section 4.1 review on page 89. If you have any questions, let me know. Bye.